All right, so we'll get started now. And at first, there is some confusion about the assignment. There's some duplicate problems on the assignment. I'm not going to tell you which ones they are, but there are duplicates. If you find a duplicate and you solve the problem at an earlier point, you can simply refer to your earlier solution. So if 9 was a duplicate of 7, inside 9 you could say, see my answer for 7. That's okay. But if you put down two different answers for 7 and 9, then we are going to grade those separately. Is that okay? All right. So that's that issue. The other issue is that I've delayed the due date for assignment 3 to Tuesday night, at the end of the day Tuesday. That's because we have room to cover more of the material that's in assignment 3. So we don't have to make it due last night. So I don't know if you received that message or not. I did send that note out last evening to everybody through their school email accounts. How many people got that, by the way? I'm just curious. How many people get that? So most people, right? Okay. So one of the problems that's in assignment 3 is binary search. And that's something that we haven't covered yet. So we'll start today with covering binary search. And if we have time, then we'll look at some other things. In particular, two-dimensional arrays is a topic that we haven't covered in lecture, although it's in your reading. All right, here's the problem. I'm just going to approach this the way we normally approach our problems, which is to start coding up a solution and then talking about it as we go along. And the problem is to implement a function. And the name of the function is contains. And we get a vector v, so the function is contains. We want to know if the vector v has in it an integer k. So does v contain k? And so the function returns true or false. Let's look at an example. Let's suppose, here's an example of a vector with 5 elements. Say that k equals 3. Then when we call contains, that should print what? That should print true. So k is in B. There's another variation of this problem, which is maybe we instead of returning true or false, we return the position of k in V. So there's two variations there. So the other one would be something like find, say, or search. Search for 3 in V, and it returns it prints what? 1. That's the position of 3 in V. See, so here's V, 1, 3, 5, 7, 9. Those are the elements of V. And these are the indices, so I used an I there to represent the index. This is the index position of the first element. Indexes start with 0. So 3 is located at index 1, which is the second position. So this search will return the second position, which is 1, the index value 1. I know that's confusing. Okay, and now if we call contains with 4, this will print false. If we call search with 4, it prints, what would you print? What would you print if you were going to design that search function? What do you think? Well, I'll tell you, there's a standard conventional return value for this function. It's not just for binary search or searching, well, mainly for searching, finding an index of something that's not in the collection, that's not in the array. What do you return when the thing you're trying to find is not in the vector? Take a guess at what the convention is.
-1.
-1, that is correct. I mean, we could have returned -3, right? But we cannot return 0. Because 0 is a valid index. That's the first position. So by convention, programmers return -1 to indicate that something that's being looked for in a sequence is not there. If you're looking for something that has an index, has a position, an integer position, return -1 if that thing is not there. But today, and I want to warn you, you need to be ready for this on the quiz. I may ask this one, or I may ask this one. These are the two variations of the binary search problem. The algorithm is the same. The implementation is only slightly different, just a tiny bit. The difference is negligible. So they're essentially equivalent. And I'll show you this first one, and I will not show you this one today, but you'll need to be prepared to solve that problem for the quiz. All right. Now, this is a vector of 5 elements, and we're also going to look at a vector of 3 elements. And so I'm sorry, 4 elements. It turns out that it's a little bit different for an even number of elements versus an odd number of elements. All right. Let's see if this thing builds. We have some test code already. We have the function defined here, contains. We need to return a value. Return true. And we should call it here. Well, we don't have a vector yet. So let's create a vector. A vector of int. Say v5, I'll call it. Push back. What's it? 1, 3, 5, 7, and 9. 1, 3, 5, 7, and 9. I kept it on the odd numbers to make so there was a gap between every value, and just so that my note would be easier to look at my sample, I kept it to 1 digit. All right, so we want to assert that we call contains with v and 3, that it returns true, that v does contain 3. I need the vector header. And this should work because we have a stub that returns true. Oh. Use of undeclared identifier V. Right, use V5. Does V5 contain 3? It should be true. Still a problem. Oh, the parentheses are wrong. There we go. All tests passed. Now we need to figure out how to find the thing. We could do a linear search. We could do a linear search. We just let I range between 0 and the last valid index. And if we find it, if V of I is K, we return true, we found it. Otherwise, we didn't find it. Is this a homework problem? This is an assignment problem, right? It should be, if it isn't. Yeah. So you need to know this. That's a linear search. Now let's suppose that the elements of V are not in sorted order. This is the search you have to use. If the elements of V were in any arbitrary order, we would need to look at each element one after another and to see if the element, the value that we were looking for was in one of the elements. If we found it, we returned true. After looking at every single value, we didn't find it, then we returned false. That's a linear search. Imagine if you had a telephone book and the book had all of the names and phone numbers of the people living in your town, and you wanted to look up someone in the book. Well, you'd perform a binary search. I know you don't use phone books anymore. It's hard to get a good example these days, but that's the one I'm going to use. And so you split the phone book in half, or you estimate where you think the last name is. It's Gomez. Last name is Gomez, so you're going to go a little bit to the left, but not quite in the middle, somewhere. You just open it up, and then you say, well, did I open it up to a page? Is Gomez in the left part or Gomez in the right part of what I'm holding? Is it in the stack of the half of the phone book that's in my right hand or the half that's in my left hand? And then you say, oh, it's in my left hand because I opened it up to the M's. So I'm going to split the thing that's in my left hand now, and you keep splitting. That's called a binary search until you find the page that has, that you can determine, oh, Gomez doesn't live in this town. There is no Gomez here. Or, oh, there's the Gomez. There he is. Or there's multiple. That's another issue. So that's called binary search. But now imagine that the telephone book, that the names were just in a random order. So, B didn't follow A anymore. A could be anywhere. So how are you going to find Gomez now? If you do a binary search, how are you going to do that? You'll be like jumping all around and never getting there. So you have to do what's called a linear search. And so you'll start with page 1, or you can start with any page, but you have to look at every single page to know that Gomez is not in the book. So if the vector of elements is not sorted, you have to do a linear search. But if the vector of elements is sorted, then we can find the value much more quickly. Instead of looking, if the vector has n values, if it has 100 values, and it's not sorted, in the worst case, we're going to look at 100 positions in the vector. But if the vector is sorted, then in the worst case is the value that we're looking for is not in the vector. That's the worst case, because we have to keep looking until we have reached the conclusion that it can't be here. And so in the worst case, if it has 100 values and you're doing binary search, then it's going to be the log, or roughly, plus or minus 1. The log of 100, log base 2 of 100. What's a log base 2 of 100? Like 9, something like that. It's like around 10. So, no, it's not that much, right? It's more like 8 or 7, something like that. So it's a number. The search time is dramatically reduced. The log of a number is a lot smaller than the number itself. Right? What's the log of 1024? What's the log base 2 of 1024? Anybody know that? I think I know that. 10, right? 2 to the 10. And so 10 is a lot smaller than 1,000. And as the number gets larger, the log of that value is reasonably small. So it doesn't take a lot of work to find something in a sorted list. But if the list was not sorted, it would take a much longer time. And that's a big problem in data processing. And that's why there's a lot of attention, a lot of work done internally in data processing systems to keep values in a sorted order. Because when you have to look something up, you can get to that value much more quickly. All right, that's enough on that. How are we going to do this? V is sorted, so this linear search is not going to work for us. We need to do a binary search. So here's the vector. And let's suppose we want to search for the value 3. So k is 3. We want to find 3 in here. And we want to use a binary search as if we were looking through a telephone book. So when we do that, we have to keep track of 2 variables. One is the start position. So we're going to be right now, we're concerned with this whole range, position 0 through position 4. We don't know. K may be at any one of those positions when we start the algorithm. And now, we're not going to just check S and then S plus 1 and then S plus 2. So S is 0 now, and E is 4. So those are index values. S points to the leftmost index position that we haven't yet checked. E is the end. It points to the index position that the rightmost index position that we haven't checked. And we're going to sandwich this. So we're going to bring S and E closer and closer together until we hit the K that we're looking for, or else we can conclude that K is not in the vector. So to make this thing work, we have to look at something. And what we're going to do is we're going to compute the midpoint, M. And we're going to look at the value at the midpoint, which happens to be 5 here. So we have an S and we have an E. And then we compute the midpoint between S and E. And we're just going to look at that. is that K? Well, no, it's not K. K is 3. Well, is K to the left of the midpoint, or is K to the right of the midpoint? Well, in this case, K is to the left of the midpoint, because if K is, without looking to the left, the midpoint is storing the value 5, and it's in sorted order, so we're looking for 3 that's less than 5. 3 is less than 5, so it must be to the left. So what do we do there? In the next step, we adjust. Let me do it like this. We have S and E, and then we compute the midpoint, M. And then in the next step, we move E to 1 less than the midpoint. See, we don't want to move E to the midpoint. Remember, we're squeezing S and E together here. We don't want to move E to the midpoint because we checked the midpoint. We know that K is not at the midpoint, so we're going to move E 1 less than the midpoint because that's the largest number that might be K. We know that K is not at M. And so we'll move E to 1 less than M, and E, the number may be at that value actually, and then we hit it, we get it right away. Then the next iteration of the loop, we have to compute the midpoint again, that's the thing. Now we have S and E. I mean, it depends how you write the code. You could write the code so that, oh, S and E are 1 apart, let's just check S, and then we'll check E, and then we're done. You could write your code like that, but it turns out you can make even more compact code. If you don't stop at this point and you compute a midpoint, what's the midpoint between 1 and 0, 0 and 1? What's the integer midpoint between 0 and 1? Well, the average between 0 and 1 is a half, but there's no half index, so we usually have truncation when we do division by 2. So to compute the midpoint, you take the average of the two values. The average of 0 and 1, the position 0 and 1 is a half. And that truncates to 0. It's an integer division. We need an integer value. We can't handle a fraction because the thing's got to be is an index. And so now let's check M. Is the value K at M? Well, no, it's not at M. Because K is 3 and the value at M is 1. So that means what we have is that K is larger than the midpoint. That means we're going to move S 1 past the midpoint. Well, that means S and E are now together. And S and E are now together. I'll put an X there. I can't. Unfortunately, I just have one character. X means, I didn't think about that problem. So X equals S and E together. So now, if S and E are together, what's the midpoint? If they're the same value, well, that's their own. The midpoint is right there. S and E are equal. The midpoint is there. We find it, and we determine that. Yes, K is at the midpoint now. So we're done. We return true. Let's look at another example. Let's suppose we were looking for 2. 2 is not in there. How does the algorithm work when 2 is not in there? S is set to here, and E is set to the end. I'm leaving the indexes out now. Then we compute the midpoint, which is here. And we compare 2 to the value at the midpoint. 2 is less than that, so we have to bring E down to 1 less than the midpoint. Now we compute the midpoint again. We have that integer division with truncation. The midpoint is at 1. And we look at the value at M, which is 1. We compare it to 2. Well, 2 is larger, so we're going to bring S up. Now, S and E are the same index. Now we compute the midpoint again. And we look at the value at the midpoint, which is 3, and K is less than 3. That means we move E to the left. So E is now there, and S is there. That's where we terminate, when E is less than S. We don't need to look anymore. You see how that works? That's the algorithm. So we have the start point, which is 0. We have the end point, which is v dot size minus 1. And we want to loop until we reach that termination condition. Loop while S is less than or equal to E. As soon as this condition is false, then we won't execute the loop anymore and we'll return false. So what do we do inside the loop with each iteration of the loop? Can anyone suggest to me what we would do first inside this loop? Oh, sorry. Can someone suggest to me what is the first thing we're going to do in this loop? What do we need to do inside that loop? Yeah.
Check if E is equal to K.
Check if what?
Check if E is equal to K.
Check if E, no, we never check to see if E is equal to K. We check to see if the value at the midpoint is equal to K. We never check the value at E. We never check the value at S. We only check the value at the midpoint. What's the first thing we need to do in that case?
S plus E divided by 2.
Huh?
S plus E divided by 2.
Yeah, calculate the midpoint. We need to calculate the midpoint, right? And then we can check the value that's at the midpoint. That's it. Thank you. So it's start plus E divided by 2. We calculate the midpoint with that, integer division, so we get truncation. Now we can test. Now we can test if V of the midpoint is K. Do we find it? If we did, that's great. Turn true. And in the other case, we return the midpoint. But what happens if the value at M is not K? Then we got to check to see if the value at M is the value at M less than K. You could do greater than K2. If the value of M is less than K, then we're going to we need to adjust is it S or E that we have to adjust? E? If M is, so K is bigger than the midpoint.
Oh, then you S.
Oh, S, yeah. Thanks. By the way, I usually get that wrong every quarter I teach it. I got to go back and debug. So I let you decide this time, and you got it wrong, not me this time. But we haven't tested yet, so we're not sure. So S equals
So is that N plus
what? Huh?
N plus 1?
M plus 1. Very good. Thank you. Excellent. But let's suppose that V of M is not K and is not less than K. Then what are we going to do?
Then you do opposite.
Huh?
Then you do V of M is greater than K and you do minus 1.
Then you do what?
Or S equals, or not S, E equals N minus 1.
E equals M minus 1.
V of M is greater than K.
But we know it has to be greater than,
Oh, yes. No,
V of M has to be greater than K because we know it's not less than K and it's not equal to K, so it has to be greater than K. We can put an assertion in there if we want, but, so it must be the case. It must be the case that, V of M. But, if that's a little weak, in your mind, and not really, you want to make sure, then you could just toss an assertion there. Let's do that. Just to make sure that we're not making any mistakes in our reasoning. Let's throw an assertion in there. Another way to do it is we could have another else if with a final else that throws an exception saying something's wrong with our thinking. But this will do it too. It's nice to have these. By the way, that this is in a macro, that when you build your code in what's called debug mode, that the assertion will be included in the compiled executable. But when you compile in what's called production mode, to deliver to the client, to run your video game, on your customer's PC, then the assertions are actually removed because it takes compute resources to execute the assertions in your code. So they're only used for development purposes. And I think, actually I'm not sure about C++, how that works. I think they're removed when you do a production build, but I'm not sure actually. I think it depends on your compiler and the compiler settings and so on. So that you would have to research that to be sure about in the development environment that you're working on, whether the assertions are removed when you compile for what's called a production build. All right. That's it, isn't it? Right there. Oh, no, it's not. Oh, yes, it is. Here, look, we either return true here or we return false here. There's always a chance that we have a mistake in our logic and we get into an infinite loop. Right? That means we would never terminate. Now, let's try this. No problems. I'll test pass. It works. If we had some mistake in our code, like maybe we got that wrong. The thing is, we don't know if the test code is adequate. Oh, look at that. What's happening? Who can describe this This is what's happening, huh?
Is your loop never ending?
It's an infinite loop. The loop is never ending. Yeah, so we usually say infinite loop. Or in the, I got to do, how do I kill an infinite loop when it's running? Control C. All right. So then we have to go back in and we need to investigate. And we say, oh, we made a mistake there. And let's fix that. Okay. Let's try the other vector. You know, the vector of size 4 is it's not that interesting, but it's just the starting point of the algorithm. You have a truncation in the first step rather than in the second step. So I think this is actually good enough as a test. I think that's enough. I don't need to do this case. Oh, I call it contains here, right? Here I say binary search. I meant to call it binary search. Sorry. This should be called binary search. And I'm going to use the word contains for the maybe the linear search. That's what I meant. I'll have to fix this later. Okay, I meant to use this word, not contains, but binary search. All right. What about the running time? And I talked about the logarithm, that the number of sort of iterations of your loop is roughly equal to the log base 2 of the size of the vector. And let's take a look at that. Let's count how many comparisons we're doing. All right, let's take a look at that. And I think I'll take this out just to tighten it up a little there. And then this is not going to work. So that code is tested. For I equals 0 to, say, 10,000. Let's do this. We'll push back, say, 2 times I. So we have an increasing sequence of values, all the even numbers from 0 to 20,000. I'll use an assertion here. Assert binary search V, and we'll put in a number 1. So when we start splitting down the middle, we're going to split to the left. So we have to do a lot of splits. Actually, it doesn't matter where we put it. No, I guess it does. This will make it run the longest, I think. Is that right? Yeah. So pushback, oh V, it should be V5, that's a V. What's the issue there? Unterminated function like macro invocation. Line 24. I'll just jump right to line 24 and fix that right there. Okay. 10,000. It's going to take a while, right? We can go out and have a cup of coffee. Whoop. Assertion failed. Oh, this should be false. All right. This should work. Time to go get a coffee. Wow, that ran fast. Drank that coffee so fast. It runs pretty fast. What if we did a linear search? It's interesting when you do linear search and you start bumping the number up. Binary search keeps finishing like immediately. The linear search starts taking a little longer. So how about the, let's do this. Let's have 1,024 elements. And log base 2, what's 2 to the 10? 2 to the 10, right? That's 1K, right? So that's 1,024. And is that right? 2 to the 10? Is that 2 to the 8? 2, huh? 2 to the 10, yeah. I don't know why I'm doubting myself right now. 2 to the 10. And so this loop should run about 10 times, right? Let's test it. Let's put a counter in there. Set it to 0. We'll just print the counter. Oh, 10 on the nose. Yeah, so 2 to the 10. It's like if you start with 10, you know, it's the opposite. If you take 2 and you double it 10 times, you get a 1024. But if you start at 1024 and you divide by 2, you're going to go back down to 1 in that in the same number of steps. So that's that. And what did I ask for? Check that it completes in that many iterations. Use the assert function. So I think what I meant to do there is this. Assert that, well, we'll do it like this. When we're ready to return, we want to assert that the log base 2 of our counter, of v.size. Log base 2 of the size of our vector is less than or equal to what am I doing here? Oh, the counter. The counter is, sorry. Yeah, not sure about the way I have this assignment, whether it's clear for people. The counter should be less than or equal to log 2 v.size. I think you need to put a +1 in there. Let's just throw it in there. And this log 2 is in, I don't think I need it on my system, but I think you might need CMath. Is that what I said here? Yeah, CMath. And I think in the labs you need to use that header. Okay, I got a lot of errors, but I like to look at the first error first, because maybe the ones following it will be fixed once I get the first error fixed. Unterminated, this is the same problem I've been having, isn't it? It's a missing parenthesis. Line 19. All test paths. Yeah, I'm trying to get people to use assertions, in your code, and sort of get the hang of that. But this is not the only place where we return from the function. We also return here. So you should put it in here as well. So 0 is in that vector. Looks good. I used 1 and 0 so that I would just keep splitting downward, although you could use other numbers to get the same result, I believe. Can you? Maybe not. Any number works. Every number does the same thing, doesn't it? So if we used, say 501, we're going to get the same behavior. We're going to get the same number. The count is going to be the same. Oops, sorry. The count will always be the same when we I think we're going to get the same thing. Well, we don't find it. This one here. If we do find it, we might find it right away. We might get lucky. But if we don't find it, I think we have to do the same number of looping operations. See, it doesn't matter what number we're looking for. If it's not in there, it's going to take 10 iterations of that loop to determine that. On the other hand, if it's in there, then we might get a shorter, less numbers of iterations. Let's do an example. Like, let's suppose it was at well, let's see, when we take 1024 divide by 2, we get 512, right? So we're going to check 512. So it would be 1024. Because we put in double of everything. Let's see if that works. Still 10. I don't get it. So when we find this, it still took 10 iterations to find that. Is that right? How can we make it run once? see, the numbers that are in there are 0, then 2, then 4, all the way up to 2048 minus 2. And so 2000, so maybe it's off by 1 like this. How about that? Or 4. I got it. Anyway, you can tinker with that. And you see how I'm experimenting? I guess maybe you didn't follow all that stuff right at the end there. But it's worth playing with your reasoning and the algorithm and run these kind of tests, do those investigations. Is there any questions about this? Do you want to see how to do this with the where you return an integer value rather than a bool? Did you want to see that? Because you'll need to know that. All right. Let's suppose you return an int. I want to know the position. I want to know the position of k in V. I don't want to know whether it's in there. I want to know its position or minus 1. So this should be position. What's the position of that one? I think it's I'm going to guess 511. Let's see if I got it. And so now when we return, we don't return true anymore. We return to position of k and v, which is m. So it's pretty much, it's pretty straightforward. Otherwise, we don't find it. What do we return? Negative 1. All tests passed. I got it right too. So position 111 or 511 rather. So that's how you. So it's a small change. If you want to return the position of k in V, you need to either return minus 1 or return the m where we found it at. Okay, that's it. What about back here in, where was it? Arrays. I was thinking this one might be worth looking at quickly. Does anybody have an alternative suggestion? Or do you want to see this one? Is this the right choice? Yeah, okay. And this one is this is 6. Oh, we're just skipping 1, aren't we? That's not a big deal. So we're gonna be working with this one here. Okay. The problem is this is a 2-dimensional array. This is only going to take a minute, not a second, a minute. 3 minutes. Start the timer. Okay. It's a function. Is all zeros. We pass in a vector, an array of 150 rows by 100 columns. And let's create an array. that's two-dimensional. Oh, this is a little tricky, isn't it? Can I do it like this? Does the compiler take this? Maybe it's not going to take 3 minutes. All right. Oh, that's 50 by 100. Oh, we can't do that. All right. So it's 50 by 100. So we'll have I and J. And I ranges from 0 to 49. J ranges from 0 to 99. And A of 0, 0. I'm sorry, not 0, 0. IJ. Let's give it a good one. I'll put everything at 0. And then the test is that is all zeros A is true. Now in the lab, I think you have to do this, right, with the test code. Did I ask for test code? Yeah. I didn't ask for test code, but I don't see how you're going to do it without test code. So we call the function, and it should tell us true. Let's return false in the stub. And even though the array has all zeros in it, so we just created an array. Here we allocated an array that's 50 by 100. And then we generated every possible valid index, pair of indices, I and J, and set the value at that location in the array to 0. So we made sure that the array was all zeros. So when we call is all zeros and pass in A, the function should say true, that it is all zeros. But we're, of course, returning false, so that should fail. Now let's check it. And it's going to look just like the test code. And it looks like this. So let's look at everything in the array. We have to look at everything. If each value at I and J is 0, oh, see, I'll tell you, this, you as a student will get confused about this. So I'm going to simulate being confused about this. So I want to make sure each value is a 0, and if it is, we're going to return true. You see the problem with that? We have to look for a non-zero value and then return false. If we find one bad one, then the whole barrel of apples is bad. But after inspecting every single apple and we just found no bad one, then we can return true. So we can't do it the other way. You can't go Aij equal to 0 inside the loop. That's not going to give it to you. And it's really common over the years. I see so many students, that's the road that they travel down, and you have to sort of recognize that. Okay, so this should pass now. Good, that's it. And what happens if we put a value in there like 3442, and we set that to 9? Then this should fail. This should now be false. It's not all zeros anymore. One of the values is a 9. So in our test code, we check to see that the function returns false. It looks good. All right, that's it. That's how you use two-dimensional arrays. Anything else? Sorry, got a little boring. If you were doing this up down here, it'd be more interesting. So, but that's what we're going to do in lab. So in lab, it's your turn to play and get these solutions produced. Anything about the quiz? Or let's see. On Wednesday, we're going to cover the answers to assignment 3, and then just move forward if we have any time left over after that. Okay? And the quiz is on Monday. Assignment 3 is not due yesterday. It's due tomorrow night at midnight. That's it.
You changed the due date.
What's that?
You changed the due date.
I changed the due date. Is everybody clear about that? Okay. The assignment 3 is due tomorrow night. So if you've already submitted it, it's not a problem. Jaren is ready to receive your submission a second time. So you can send in a second submission.
I actually emailed in the answers to it, so you want me to go into lab and just send it to Git or?
If you submit through Git, which is preferred, then send them an email and say, ignore what I sent you in my last email, get my answers from the repository. That's good.